All right, so we're going to take a look at section 4.3, okay, which is on equations and inequalities with rational functions. Okay, so basically the goal is we're going to take equations and inequalities that contain rational expressions, so fractions that have polynomials in the top and the bottom, and we're going to solve them. Okay, we'll do some algebraically and we'll do some graphically. Okay, our first problem we're going to look at is going to focus on a distance, rate, and time problem. So we're going to need a formula that relates those three variables, and this is the formula. Distance equals rate times time. Okay, how many people have seen that formula already? D equals RT. Okay, so some people. Okay, so to calculate your distance, all you do is multiply your rate or your speed times your time. One thing we got to make sure of is that everything is in the same units. So if speed is in miles per hour, time would have to be in hours. Okay, you couldn't do this problem if you had a speed in miles per hour and a time in minutes. You've got to make your units match up. All right, so our first problem says Sue drove 30 miles to a train station. And then once she got to the train station, she got on a train, and then she completed her trip by train. In all, she traveled 120 miles. That includes the 30 miles she drove by car, plus the remainder of the trip she did on train. Okay, we don't know the two speeds. We don't know the speed of the car, and we don't know the speed of the train. But what we do know is that the average rate of the train is 20 miles per hour faster than the average rate of the car. Okay, so let's suppose we let x equal the speed of the car. If x is the speed of the car, and the train is going to go 20 miles per hour faster than the speed of the car, what would be the speed of the train? The speed of the car is x, and the train is 20 miles per hour faster. Victoria? So the speed of the car, we'll let that be x. What would the speed of the train be?
20 miles.
20 miles per hour faster than a car. So what did we say we're going to let the speed of the car be? X. And now the train is 20 miles per hour faster than that. So what would the speed of the train be? It won't be a number. It's going to be a variable expression.
20. Or is it x plus 20?
X plus 20, yeah. Okay, so the train is going to be x plus 20. Okay, we're going to need that fact. And we're going to use that to find an algebraic expression for the time that it's going to take to complete this trip. All right, so first thing we got to figure out is how many different times do we have? Okay. Well, she's going to be traveling by car for the first part and by train for the second part. So we have two different times we have to add up. So the total time for the trip is going to be the time, we'll call it time in car, plus we have to add the time she's on the train. Okay, so we have to figure out these two things. Let's look at our formula again. Distance equals rate times time. what we want to do here is solve it for t, okay, because we have to figure out some times. Okay, how would we get t by itself in that equation? James?
Divide by r.
Good. Divide by r. Divide by r. So if you take your distance and you divide by your rate, you get your time. All right, so let's figure out the time in the car. So the total time, which I'll call t, is going to equal time in car. So we need the distance we travel in the car divided by the speed we travel in the car. All right? To figure that out, it might be helpful if we make a table. Okay? So we've got car, train. And this table will just help us organize everything we need. So we have the distance we travel in the car, the distance we travel in the train, and the speed we travel in the car, and the speed we travel on the train. Okay, Cody, how many miles did it say we were going to travel by car?
30 miles.
Yep, 30 miles. So Sue drove 30 miles to a train station. Based on that sentence and the next one, how many miles did she travel on the train? Cody? 90. 90, right?
90.
Yeah. So she traveled 30 miles on the car, 90 miles on the train. That's your total of 120. All right. Now we're going to figure out our speeds. Okay, Alex, what did we let the speed of the car be?
X.
Yep. The speed of the car is x. And do you remember what we said about the speed of the train?
X plus 20.
It's going to be x plus 20. Okay, so if you have trouble thinking about all that, maybe a table helps you just to organize everything. Now let's write our equation. Okay, let's start out with the distance we traveled in the car. That's 30. And we're going to divide that by the rate, x. So there's the time in the car. 30 divided by x. Plus, Augustine, what's our distance that we did on the train?
90. Or 120.
Oh, I'm sorry. Yeah, that is 90. No, you're right. The total was 120. I think we said 90. Yeah, you're right. Okay, and we're going to divide that by the speed on the train. Colby, what's our speed on the train?
X plus 20.
X plus 20. And that's it. There's a formula that'll give you the time for this trip as a function of x, which is the speed of the car. So if you're going 50 miles an hour, plug in 50 for x, you could find out the time. Any questions on that equation? All right. So let's look at that equation a little bit more, and let's find some of the asymptotes, the end behavior model. Let's find the roots, or the zeros, and then we'll graph it on the calculator. The first thing I want to do is rewrite this. Okay, this form is going to come in handy. Okay? But if we rewrite it with a common denominator, that's going to help us to do some other things. Okay, so what would my common denominator be here? Andy? How do you find, like let's say I said to do 3/4 plus 5, let's say, ninths. What's one way you could find a common denominator? Might not be the smallest one, but it'll work.
You could multiply
Yeah, multiply.
the 4.
Yeah, you just multiply the two denominators together. Again, it might not be the smallest one, but it will work. We're going to do the same thing here.
X, or X squared plus 1.
Yep, sure. If you want to do the whole thing at once, we can FOIL it out. For now, I'll hold off and just write it as x times x plus 20. All right, so now we got to figure out, all right, what do we multiply the first fraction by? We got to multiply by x plus 20 on the top, x plus 20 on the bottom. Okay, what about my second fraction? What would I have to multiply top and bottom by there? Yeah, Emily? Yeah, just x and x. Okay, so now let's do that out. We're going to get 30x plus 30 times 20 is 600 plus 90x. Okay, so all we did was combine and get a single denominator. And how about James? Anything else I can do now on the right-hand side?
You can combine 30x and 90x.
Yep, we can combine those, and what do you get?
120x.
Good. So we combine like terms, you get 120x. You can leave the denominator factored. That's fine. All right, so we'll come back to using that to find probably the end behavior model. That'll come in handy for that. And also probably for the roots. Okay, let's start with the asymptotes. Let's do the vertical asymptotes. So the vertical asymptotes are the values of x that would make the denominator what? 0. Okay, so we're looking for the values of x that are going to make the denominator 0. So this is going to be 2. Jill, do you see one of the two asymptotes?
0.
Yep, 0 and negative 20. Now, when we find a complete graph, that negative 20 is important. It's part of the picture. But in real life, we'd never have a speed of negative 20. So it's important for the algebraic part, but it's not important for the real life part of the problem. All right, horizontal asymptotes. What's the thing that we usually find that helps us to get a horizontal asymptote? The what? Yeah, the end behavior model. Good. So let's find that. And then we'll come back to our horizontal asymptote. Okay, the end behavior model. For that, I'm going to go to my version of the formula where everything's combined together. Okay, first thing I want to do is look at the numerator and find the highest degree term there. How about Cody? What's the highest degree term in the top? Yep, 120x. And someone else tell me the highest degree term in the bottom. Be careful because you'd have to FOIL this out to see that clearly. Yep?
X squared.
It would be x squared. Okay. Since we have more x's in the bottom than the top, what's going to happen is we're going to have 1 cancel from the top, 1 cancel from the bottom, and we get 120 over x. That's my end behavior model. Now, if you let x get really big, whatever happens to this fraction, that's my horizontal asymptote. Okay, Cole, what happens if you take 120 and start to divide it by a bigger and bigger and bigger number? And what value will it approach? Yep, this fraction will approach 0. Which makes sense because that's my time. As you start to go faster and faster and faster, your time will approach 0. Right? But can your time to travel between two distances ever be 0? No, not unless you can like instantly teleport from one place to the other. All right. So time is always going to be a positive number. Never quite 0, but close. It can get close. All right. So we got our asymptotes. Let's find. We get the end behavior model. Let's do the zeros. zeros. So the zeros are when you take that fraction, set it equal to 0. What's the only way a fraction can ever equal 0? What has to happen to make a fraction 0? Oh, Andy?
There has to be a 0 in the denominator.
Not the denominator. That's if you get that's your vertical asymptotes. Yeah, and then numerator. Okay, if you can make the top 0, that'll make the fraction 0. Okay, so let's set the top equal to 0 and solve it. Okay, if you solve it out, you're going to get x equals -5. You'd subtract 600, and then you divide by 120. And you can check it by plugging it in. 120 times -5 is -600, plus 600 is 0. Okay, any questions on how we found everything there?
You did the zero.
Yep.
Why would it be negative one if you subtract one and the exponent?
Why wouldn't the, have a negative exponent? You could. This is the same thing. But generally, we try to write it without negative exponents. So we use our rules from Algebra 1 to take that negative exponent, put it in the bottom of a fraction, and then it becomes positive. Any question on that? But she's right. It is equivalent to 120x to the -1, but we'll always go with that. All right, now let's find our graph. Okay, so I already have it typed in. Okay, we have a vertical asymptote at -20, so we want to go at least that far over. Our maximum, well, that's the speed. Okay, our speed could go theoretically as high as we want. Let's just try 50. We're just trying to get an idea of that asymptote approaching 0. For my minimum, let's do -50. Now, I understand that y value is time and negative time doesn't make sense, but it asks for a complete graph of the equation. Forgetting that this equation is about something in real life. They just want to know a complete graph of the equation. All right, and I think everything else looks good. Let's graph it. Okay, so that looks pretty good. If we were graphing just the real life part of this would all be in quadrant 1. Okay, what's happening to the left of the y-axis, that wouldn't be in the real life situation. Maybe you want to set your x-min a little bit more negative so you could see. There's your asymptote approaching 0 on the left, approaching 0 on the right. Get your vertical asymptote at -20 and at 0. Okay, so there's a good complete graph of that. Any questions on that? All right. So now using that graph, I want to figure out how fast she has to go to complete the trip in exactly 2 hours. We'll do it 2 ways. First, we'll do it graphically, and then we'll do it algebraically. Yeah? The other graph?
Yeah, just
Yep. So we've seen this kind of pattern before where you get that S shape in the middle. You check the behavior on each side of the asymptote. So this graph is really in 3 sections. Okay, how would we use this graph to find out how fast she has to go to complete the trip in 2 hours? What would we have to do? of Alex? Keep in mind our y value, what does y represent in this problem? Y is time, right. So all we have to do is look at doing something, another equation for y. To find the speed, yeah, we have to add an equation to this picture. We need this one, but we need one more. And we're going to look for something special. Sure? Yep, Brianna?
I would say y speed is over x speed.
Y is time.
I mean, yeah.
X is speed.
X is speed.
Yep, X is the speed of the car, not the train. Anybody see what we'd have to add to Y2? Oh, Augustine?
What?
What would we have to put in Y2?
Why would we have to put in Y2?
Yeah, what? I want to solve this problem. You just get 2 hours to complete the trip.
You just put in 2.
Yeah, you just put in 2, and then what?
And then you find the intersection.
Yeah, we find the intersection. Okay, it looks like it's pretty close. It's hard to tell if they're intersecting. Let's try. They do intersect, but I'm not sure if it's on my screen. Yeah, I guess just barely. So it's 46.46. If she wants to complete the trip in 2 hours, that would be the speed of the car. 46.46. All right, let's solve the same thing algebraically. Okay, to solve it algebraically, just take your equation we just had. Don't set it equal to 0, set it equal to 2. Let's see if we can solve it. All right, first thing we want to do to solve that is try to get rid of that fraction on the right. Okay, so Brianna, what could I multiply both sides by to get rid of that denominator? Yep, x times what? Yeah. Okay, and if we do it on the right, we also have to do it on the left. Okay, so that's going to cancel. And on the right-hand side now, we just have 120x plus 600. On the left, we have a distributive property. We have 2x squared plus 40x. I just distributed 2x to the x plus 20. What kind of equation is that now? Look at the highest degree exponent. That gives you a hint at the type of equation. Casey? Okay, if we draw it, it's a parabola. And that, what is the name of that equation? Equations that create parabolas are called. Remember that? Yeah.
Quadratic.
It's a quadratic. Okay, so now we have to solve a quadratic equation. Right? There's a couple ways we could solve it. Sometimes factoring works. I don't think factoring is going to work here. So what can we do to solve a problem if it's a quadratic and you can't factor? So, Kobe? Think about from Algebra 1. How do you solve a quadratic if you can't factor? I'll give you a hint. You can complete the square, but I don't want to do it that way either. So we're solving a quadratic equation. So you can factor. You can complete the square. You could do it graphically, but we're not going to graph it. But there's another method to solve a quadratic. That's a hint.
I got
Quadratic formula.
The quadratic formula. Okay. Quadratic formula. Okay, so now my next question, if you're going to use the quadratic formula on this equation, we can't do it the way it is now. What do you need to have on one side by itself? What number? 0. So get this equal to 0. Okay, so we got 2x squared. Bring our x's to the other side. What could I do right before I use quadratic formula here? Something that would make the numbers a little easier to work with. Let's see. Cole, you see?
Factor out of 2.
Yeah, you could factor out a 2, divide everything through by 2. Same idea. And now we have that. Okay, I'm not going to go through the quadratic formula. You guys really have to know how to do that from algebra, but I will give you the two answers. So you'd use quadratic formula. And the two answers you're going to get are 20 plus 10 root 7 and 20 minus 10 root 7. Now, let's think for a second about what the square root of 7 would be. What two numbers is the square root of 7 between? Oh, James?
2, 3.
Yeah, it's somewhere between 2 and 3, but it's bigger than 2, right? If you take a number bigger than 2 and multiply it by 10, you're guaranteed to get a number bigger than what?
5.
Bigger than that. Take a number that's, we know it's at least 2, it's even a little bigger. But if you take even just 2 and multiply it by 10, what do you get?
Oh, multiply the
20, yeah. So we're guaranteed that 10 times the square root of 7 is bigger than 20. What does that mean about this second answer? If I do 20 minus 10 square root 7, what's going to happen? It's going to be negative. Can we have negative speed? No. So this second answer doesn't work. And graphically, we saw the second answer earlier. It was right kind of in that spot right there. All right. If you type this in, 20 plus 10 square root 7, you will get 46.46, the way we did it graphically. All right, so we did something in this problem that we have to be careful of. Okay? We multiplied both sides of the expression that we had by a variable. Okay, that was one of the first steps we did. We multiplied each side by x times x plus 20. If you do that, you might end up with an equation that's not equivalent to the original problem. And what that means is you may get extra answers to that equation that are not answers to the original problem. And those are called extraneous solutions. Okay, an extraneous solution, it's an answer to your new equation that you formed by multiplying both sides by variables, but it doesn't answer the original problem. So what that means, you've got to double check your answer. Okay, you have to plug it in, check it, see if it works. Okay, let's look at this one. Very, very simple equation. X minus 1 equals 0. If you were to solve that equation, x minus 1 equals 0, Brielle, what do you get? You get x equals 1. That is the only answer. But watch what happens if you multiply both sides by x. Okay, because we've always learned, as long as you do the same thing on both sides of an equation, that keeps it balanced. So let's try that. If you multiply by x on the left, you get x squared minus x And if you multiply by x on the right, you still have 0. 1 is still a solution to this problem. 1 squared is 1, take away 1 is 0. But does anybody see what other number you can plug in? That's also a solution now? Yeah? Let's try. -1, if you square it, -1 comes out to +1. Yeah, and then if you take away -1, it becomes a +1. So that would come out to 2. Yeah? 0. 0 is a solution to this new equation that I formed by multiplying both sides by x. But 0 is not an answer to the original. This is called an extraneous solution. So anytime you multiply both sides of an equation by a variable, check and make sure that your answers work back in the original problem. In this case, the only one that works is when x equals 1. Okay, any question on that? Okay, and that'll only happen if you multiply by a variable. If you don't multiply by a variable, that won't happen. All right, so let's look at this problem. So I want to try to solve this. We'll do it two ways. We'll do it algebraically, then we'll do it graphically. And the goal this time is going to be to eliminate the fractions. I don't even want to find a common denominator. I want to get rid of the denominators. Okay, and the idea is similar to this. If you had 2/3 plus 5/4, and that was equal to 7/12. Now let's throw a variable in there somewhere. And I asked you to solve that equation. If you multiplied everything here by 12, times 12, times 12, and times 12, all your denominators would disappear. Because then 3 would go into 12, 4, and leave you with a 1 in the bottom. 4 would go into 12, 3, and 12 into 12 would cancel. So what we're doing is multiplying each term by the same thing. Okay, let's try the same idea now with this. There's a connection between these denominators, and in the problem I just had up, I had the same connection. Anybody see what the connection is between x minus 1, x minus 3, and x squared minus 4x plus 3? And a hint is to think of like 3 and 4 compared to 12. Yeah.
I was going to say that the denominators are factored.
Yeah, exactly. The denominators on the left are the factors of the denominator on the right. X minus 1 times x minus 3 gives you the other denominator. So we're going to multiply everything by the LCD, which in this case is x minus 1 times x minus 3. Okay, let's do that out. We're not multiplying top and bottom. We're just multiplying each term of this equation by the same thing. And multiply this side. As long as you multiply each term by the same thing in an equation, that's okay. Did we multiply by something that contained a variable? Oh, Emily? Did we multiply by something that contained a variable? Yep. So if we multiply by something that has a variable, Colby, what do I have to check for?
What was the question?
If we multiply by both sides of an expression by something containing a variable, what do we have to check for? Anybody remember what that's called? Yep.
Extraneous solution.
Right. Okay. If you multiply both sides of an expression by a variable, you might get extraneous solutions. Okay, so let's do it out and see what happens. The x minus 1 and the x minus 1 are going to cancel. Okay, here, the x minus 3 and the x minus 3 cancel. And here, if you realize that this factors is x minus 1, x minus 3, it cancels the whole thing. Okay, so now on the right-hand side, all we have is a 2. Okay, what about on the left? Andy, if I distribute out 2x to what I have left, what do I get?
2x squared minus 6x.
Good. A lot of people forget that they need to distribute that up. But it's 2x squared minus 6x. Okay, the next one I have to distribute out just a 1. So it's plus x minus 1. And on the other side, we've got 2. Okay, so Casey, what kind of equation is that? Yes, that's a quadratic. And what number do we like to get on the right-hand side when we're solving it? Good, want to get 0. Okay, so let's bring the 2 to the other side. So we get 2x squared. Combine your x's. Negative 6x plus 1x gives you negative 5x. And negative 1 minus 2 is negative 3. Okay, and I think this will factor. It's going to factor as 2x plus 1 times x minus 3. Let's check it. It's 2x squared minus 6 plus 1 is minus 5, and yeah, that's how it factors. Okay, what do I do with each individual factor now? Yep, Priya? Yep, set each factor equal to 0. So the first one is 2x plus 1 equals 0. And the other one, x minus 3 equals 0. So let's solve them. We get negative a half and 3. Okay, now remember, this isn't a real life problem. This was just an equation I made up. So negatives are okay, but we do have to check that they work. Okay? Let's go back up and see what happens when we plug them in. Let's check 3 first. What's going to happen if you try to plug 3 into the original problem? Anybody see what happens? Yeah.
You get 0 as the denominator.
You do. You get a 0 in the denominator. So if you try to check the answer of 3, you get 1 divided by 0. What does that mean about 3?
It's not.
It's not a solution. Yeah, it's not a solution. It's an extraneous solution. 3 doesn't work. It's not that we did something wrong. It's just that it's extraneous. Now, if you check negative a half, it will work. Okay, so that I won't go through, but it does work. So on a test, if you forgot to cross out x equals 3, I'd take a point off for that, because that answer does not work. Just the negative a half. Okay. Any question on that? All right. Let's take a look at this one. This time, you know what? I think the last problem I said to solve algebraically and graphically. Let's do this one graphically instead. If you were going to solve this algebraically, you could do it exactly the same way we just did the last one. If you don't like having this term on that side, you could put it back on the other side, or you can solve it the way it is. Eventually, you do want to get everything on one side anyway, once you get to this step right here. So I think it's actually handy that they already put it on the left side for you. All right, so let's graph that and see if we can solve it. We got x minus 3 divided by x, and you know what? Let's put I'm going to put parentheses around each part. Okay, so we'll do that first. Plus 3 divided by x plus 2. And then we'll do that. And then lastly, 6 divided by x squared plus 2x. And I'll put a parenthesis before that. Yeah, the calculator might handle order of operations okay, but I think it's going to get a little mixed up if you don't put in your parentheses. And we're looking for where that graph is going to cross the x-axis. Okay, those are your roots. Okay, how many roots does it look like we have? Oh, Victoria? 3. Okay, so let's do second calc root. Okay, pick a point left, pick a point to the right, and it gives you 1, 0 at negative 0.88, roughly. Yeah?
My graph was a lot.
Looks a lot different? Okay, let me double check and make sure. Okay, so we've got x minus 3, oh, thank you. That should be divided by x. And did I miss any other divisions? Nope. All right, let's try that. Okay, does yours look more like that? Okay, so it comes out as almost a horizontal line. Okay. Horizontal line with probably some holes in the graph. Where should there be holes? 0. Let's check that. Yep, there's a hole at 0. And there's a hole at negative 2. I know that because those are the roots of the denominator. Right, so we're trying to find where this graph crosses the x-axis. Where does it cross the x-axis? Oh, Andy? Nowhere. This will never cross the x-axis. So there's no solution. If you had solved this one algebraically, okay, what would have happened is you'd have gotten 2 answers. They both would have been extraneous. Okay, in fact, if you solve it, I think the 2 answers are 0 and negative 2. Those are the 2 answers you'll get. If you check 0, it doesn't work. If you check negative 2, that doesn't work either. Okay, so it is possible that you get no solution. Okay, so you can get 1 solution, 2 solutions, or no solution. Any question on that one? All right. So using our first example, okay, about the speed of the car again, I want to look at how fast Sue would have to go to complete her trip in less than 2.5 hours. What's different about if I say complete the trip in less than 2.5 hours versus complete the trip in exactly 2.5 hours? This is a different kind of answer. Yeah,
Isn't it an inequality?
exactly. It's going to be an inequality. So it could be any speed that from a minimum or faster. So let's type our graph back in. So we had, let's see, it's 30 divided by x plus 90 over x plus 20. And I did a standard window. We might want to, we got to set the x max a little higher. Going 10 miles an hour won't do it in this problem. So I'm going to set the x max a little higher. And I'm going to mark where 2.5 hours is. Okay, so that's her speed, or that's her time getting lower and lower as she goes faster and faster. And there's our mark for 2.5 hours. So to complete the trip in exactly 2.5 hours, she'd have to go 34.88 miles per hour. So Augustine, can you use your idea that you just said since this is an inequality?
Would it be x is greater than or equal to? Would it be or equal to?
Well, it says strictly less than. It doesn't say less than or equal.
So x is greater than 3.48 something.
34.88. So if she travels at any speed 34.88 miles per hour or faster, she'll complete the trip in less than 2.5 hours. Okay, so we'll finish up with a couple inequalities. What did I do? So I typed that equation in, and I used that window. Okay, so that's the same equation we had from example, I think example 1 and 2. Hey, any question why it has to be greater than 34.88, not equal to? Okay, so that brings us to the last part, which is rational inequalities. Okay, if you solve it graphically, remember that you can have hidden behavior. So you might have to zoom in, also have to look for things off the screen. And if you're solving algebraically, the only way we can solve it is if it factors. If we can't factor it, we can't solve it algebraically, which means I'm probably going to give you a quadratic or easier if I ask you to do it algebraically. Okay, any question on that? Okay. So let's take a look and solve that one. So 2x squared plus 6x minus 8 divided by 2x squared plus 5x minus 3. Well, anytime we're going to solve a quadratic, we have to get it 0 on one side. Okay, so Kobe, how would I get 0 on one side here?
Subtract 1.
Yeah, let's just subtract 1. So we need 2x squared plus 6x minus 8. That's all going to stay the same. Except I'm going to subtract 1. Any question on that? Because now it'll be less than 0. Now I can use a sign chart and I can find roots. Now, the way it is right now, I have two separate fractions. They have different denominators. I need a common denominator. Okay, my common denominator is going to be the denominator of that first fraction. So what I'm going to do, so I don't have to copy the whole thing over again, is rewrite 1 like this. 2x squared plus 5x minus 3 divided by 2x squared plus 5x minus 3. I'm dividing two things that are the same, so that is 1. But now I have a common denominator. And since I have a common denominator, you can put it all together. So 2x squared plus 5x minus 3, and combine your like terms. So the top, actually, it's not going to come out bad at all. We're going to lose the quadratic term. 2x squared minus 2x squared. Okay, Cole, what's 6x minus 5x? Yep, just 1x. And Brielle, what's negative 8 minus negative 3? Yep, negative 5. So the top is already factored. It's x minus 5. Okay, and we need to factor the bottom. Okay, so the bottom will factor is 2x minus 1 times x plus 3. Yeah, I think we already factored the bottom before. We had something either very similar to that, if not identical. So 2x minus 1 and x plus 3. Okay, now we make a sign chart. Okay, we've done these before. Okay, Brianna, what value would make x minus 5 equal to 0? Positive 5. If you plug in numbers bigger than 5, you're going to get positives. If you plug in numbers less than 5 into this expression, you get negatives. Okay, let's do 2x minus 1. Here you get 1/2, positive 1/2. If you plug in numbers bigger than 1/2, you get positive. Less than 1/2, you get negative. And do x plus 3. Negative 3 is the root. If you plug in numbers bigger than negative 3, like 0, you're going to get a positive. Plug in numbers smaller than negative 3, like negative 5, you get a negative. And now we can take those three sign charts, put them together to make our final sign chart, which is going to have all three roots on the same line. Negative 3, 1/2, and 5. Okay, first let's look at what happens if we plug in numbers less than negative 3. Okay, into each one of those sign charts. Okay, less than negative 3, you're going to get a negative on the top. You're going to get negative on the bottom, and another negative on the bottom. So negative divided by negative times negative. What would that come out to? Yeah, that would be a negative. It's a negative divided by a positive. Usually the signs alternate. Let's just check one more section, see if we get a positive between negative 3 and 1/2. All right, so between negative 3 and 1/2, that's a negative. Between negative 3 and 1/2, that's still negative. And between negative 3 and 1/2, that's a positive. That's a negative divided by a negative, that's a positive. It's going to alternate each section. So now we can answer the question, when are we less than 0? Two different sections. We're less than 0 there and there. So we'll write our answer. Yeah, Brielle?
I was going to ask why you're dividing it to infinity.
Okay, so the answer to the problem is anything from negative infinity up to negative 3. And you could also go from negative 1/2 up to 5. The only reason we were able to do that is because we could factor it. The next one I'm going to give you is a little more complex, so we can't factor it. We're going to have to graph it. Okay, any question on how we did that? The sign chart is really the best way if you're going to do it by hand. This one.
Do the first one, okay.
Okay, because this one has a more complicated numerator, okay, you can't factor it. We're not going to be able to use the sign chart. Okay, so we'll solve graphically. What are my two choices to solve this graphically? How could I type it into the calculator? What would you? Yeah, we could do it two different ways. What if we wanted to do it more like we did this problem? What would we have to do to type it in?
So move 15 over to the other side.
Right, we can move the 15 over to the other side, and then we're going to turn it into a root problem. Or we can leave it the way it is and look at it as an intercept problem. Okay, you can do it either way. But I think we should, let's bring everything over to one side. Okay, you don't have to find a common denominator. You could just bring the 15 over. That's fine. So x to the fourth minus 3x cubed plus 2x squared plus 2 divided by x minus 2. Okay, so I put parentheses around that entire part. And then we're going to subtract a 15. Bring that over to the other side. So we're going to look for where is this graph below the x-axis. Okay, so it's graphing it. It looks like we have a couple spots. Let's see. Just double check that we have everything typed in right. So x to the fourth minus 3x cubed plus 2x squared plus 2. And then on the end you should have a minus 15. Okay. So this time, do we want to look, let's write it out. We have 0 on the right, on the left. All over x minus 2, and minus 15. All right, so what are we looking for this time? It's a little different than the last problem. We're looking for where this graph is what? Alex?
Greater than or equal to 0?
Yeah, we're looking for where it's above the x-axis. Right? So what I'm going to do is find both intersect points, and it's going to be everything except what's between them. Okay? What's between them is below the x-axis. Right, so so keep moving till you find where your cursor is. And to calculate a root. So pick a point somewhere to the left. Pick a point somewhere to the right, but try not to get that other root, because if you have two roots in the same interval it's looking, that's going to be a problem. Yeah, so somehow I must have grabbed both roots. Pick a point left, right, and see if that works. Yeah. Okay, so one of my roots is 2.22. And the other one left. Oops. Left. Right. Right, and 2.68. So we want to write everything except what's between those two values. So from negative infinity up to 2.22. And we can include it. Okay, we can include it because we have greater than or equal. And then we're going to go from 2.68 up to positive infinity. If you wanted to know where this graph is less than 0, it would just be from 2.22 to 2.68. Just the opposite of what we have. Any questions on how we did that one? Okay, again, my suggestion, always get it equal to 0. Get 0 or get it greater than or equal, less than or equal. Get 0 on one side. All right. Okay, so for tonight, you'll need a graphing calculator for a good part of it. Okay, and it's 1 through 9, 11 to 17, just odds. 20 to 24, that's all. And 24, 28, 31, and 32. Okay, all on page 244.